a inorganic chemist at Bangor. Hello, my name is Limhi and I'm doing dye-sensitized cells. That is basically a lot like a solar cell, but it relies on a dye, and there's hundreds that we could use. Pencils, you could use, just draw a bit of pencil on a glass, that would act as a dye. Or most dyes around your kitchen you could probably get some sort of reading off of. And one piece of instrumentality that's especially important, an instrument that's especially important, is this one just here that we use. It generates sunlight basically. So today I'm just going to explain the basic principles behind something called a dye-sensitized solar cell. And you would have picked that up from what I just said with it being a solar cell. It's a lot like the cells that you'll see on people's roofs, collecting the sunlight. And it worked in the exact same principle. So the sunlight comes in and it passes through a layer of glass and then it hits the dye just here. And that's why it's dye-sensitized, because normal solar cells don't have dye in. And the dye gets excited and it ejects something called an electron. You will have come across your electrons before. And so it injects an electron into this little layer here, and this is made out of titania. That's not really important, but it produces like a conducting band. It's almost like a strip of metal for you. And then it comes around here and it gets used by whatever you're using, so maybe a television or a PlayStation. And then it comes back round and it has to complete the circuit, because we know all electric currents have to complete the circuit. So it comes back here and it hits a layer of platinum on the glass, and then that platinum then gives the electron back to the dye. And so the sunlight comes in, it hits the dye, it goes past that first layer, and then it completes the circle, and then the platinum, through a layer of electrolyte, like a liquid, like a salt, and then that back into the dye, and it completes the circle.
I'm a computational chemist at Bangor. Of dyes, and in particular anthraquinone dye, which is a red dye. Anthraquinone is a polyhydroxynated dye, and by this we mean it has a number of hydroxy groups attached. We aim to produce an accurate description of the intramolecular interactions within these dyes, and in particular the hydrogen bonding. Don't confuse intramolecular interactions with intermolecular interactions. We're only looking at the interactions of the atoms within the molecule and not the molecule with other molecules or compounds. Our study focuses on constrained planar conformers of our molecule. By this, we then increase the hydrogen bonding. The average energy of a hydrogen bond within the molecule is between 5 and 40 kilojoules per mole, and this difference allows us to differentiate between the conformers that we produce. From these orientations, we produce files and input these into the computer. The computer then takes anywhere between 10 minutes and 5 hours per calculation to come up with the energies, and from these energies we are then able to analyse them and predict the lowest energy conformers. Thank you very much.
Hello, I'm Toby, another computational chemist at Bangor. For my project, I'll be using JavaScript and VRML, which stands for Virtual Reality Modelling Language, to create a program in order to generate hypersurface. One of these 3D graphs is worth 1,000 2D graphs. Think of it as the step between 2D and 3D gaming. 2D gaming can only move in left or right, or jump up and down like in Super Mario. 3D gaming, you can move everywhere. You can look up and down, move in all directions, and see the whole picture. So if you like, these 3D graphs enable us to see the whole picture of what's going on within a molecule. And that's what my project's based on.
What uses are there to the project that you're doing?
Well, what these 3D graphs can enable us to do is describe thousands of 2D graphs just in one picture. So potentially, if these 3D surfaces were split into 2D slices, they'd take up a few pages, well, tens of pages of just 2D graphs. Whereas looking at one of these, we can look at 1,000 2D graphs, for example, just by looking at one of these pictures.
Okay, thanks a lot.
Hi, I'm Bethan, an organic chemist at Bethan. I've just started my third year project at the University of Glasgow. My project is based on one of the many chemicals found in daffodil bulbs, such as galanthine, which is used to combat Alzheimer's. This is difficult and quite expensive to make, so drug manufacturers have developed a method of extracting galanthine from daffodil bulbs. The aim of my project was to design a device to detect galanthine content quickly and accurately. The design is based on a galanthine protein conjugate, which is where we join galanthine protein to make an immunogen, which is a protein which activates a response which produces antibodies. So this immunogen could be put into a host, which in this case is sheep, and when it's injected into the host, the sheep produces antibodies. Over the past few weeks I've been producing a crossloper, which is part of the molecule which goes between the galanthine and the protein, which is this in this mask here. So the next step of my project is to link the galanthine to this product, which can then link to the protein.